So what I want to do in this talk is summarize a number of the things that have already been mentioned at the workshop regarding key processes that we now know occur in most galaxies as they evolve across the cosmic high noon period. The three key aspects that seem to be a ubiquitous, robust phenomena are clumps, compaction, and elongation. I'm going to emphasize the discoveries made as part of the Candel's program, but of course these things have been seen by essentially every program that's looked at galaxies at this epoch. So Candel's is the biggest project in the history of Hubble Space Telescope, and it's also, I think, by far the most influential in terms of number of papers, number of citations, etc. The key thing was the ability to use the Wide Field Camera 3, and in particular its infrared capabilities, which go to 1600 nanometers. So in other words, H-band. This means that we can see blue light all the way to redshift 3 and pretty much the whole visible spectrum to redshift 2. So we can see old stars, not just the UV light in rest frame from young stars. That's been the key. This is the high noon period, as we called it in our popular article, and cosmic dawn, which is accessible, of course, from the UV. This is an image from the McDowell and Dickinson review in N Reviews, and the little yellow boxes are the region that HST has basically tiled with both Advanced Camera for Surveys and then also Wide Field Camera 3 as part of these larger survey regions that many other instruments have also taken data from. So first, clumps. The clump phenomenon has been seen for decades. It was especially emphasized by the Elmagreens. But now, with Candel's, we can really get a sense of how common it is. This is a slide from Yiqing Guo's talk yesterday. And let me just highlight the two key things that Yiqing told you. The first is that about 60% of star-forming galaxies are clumpy at redshifts of 2 to 3. So these are the more low-mass galaxies, 10 to the 9 to 10 to the 9.8 solar masses, the intermediate mass up to 10 to the 10.6, and the higher mass galaxies. And this is sort of a downsizing phenomenon. The higher mass galaxies start to quench and become less star-forming and less clumpy as you go down to lower redshift. But the key thing to appreciate is this is not some kind of weird special case. This is the majority of all star-forming galaxies. Also, this is data from the paper Yiqing led in 2012. There's a lot better data that continues to support this. And that is that the colors become progressively redder as the clumps are seen closer to the center of the galaxy. So there's at least presumptive evidence that there's an effect where the clumps are moving in. That's what the simulations show. And as they form, they're young and not very metal rich, and as they move in, they become older and more dusty and higher metallicity. Second point is compaction. So by studying basically the same cosmic volume at 6 different redshift intervals, the Barrow et al. 2013 paper showed that there's a motion. Of course, you never see an individual galaxy doing this, but you see the population move from diffuse star forming to compact star forming blue nuggets to quenched star forming red nuggets, and then those tend to get bigger. And then there's the slow track where galaxies never get into this corner and just slowly fade and grow. This tends to be more of the spiral galaxies. This tends to be the galaxies that have bright, bulgy centers. This was the key figure from the paper led by Guillermo. Starting down here, redshift 2.6 to 3. Very few in the quenched region, the red nugget region. Here's the blue nugget region starting to get populated. More blue nuggets, red nuggets, more blue nuggets to red nuggets. Now, almost no red nuggets, and almost no blue nuggets. Incidentally, the stars are 10 to the 43 ergs per second or higher, AGN detected by X-rays. And roughly speaking, half of these blue nuggets have X-ray detections. That's a remarkable fact also. And then the more recent paper summarizing the trend, you have these, now with the star formation rate increasing upward, you have these star-forming, not so compact galaxies. Then you get these compact, but still star-forming galaxies. And then here's the sort of path. And then quenching, and then passive evolution. So normal star-forming galaxies follow a star-forming rate, structural main sequence, compaction, triggered dissipational processes, strong core growth. So this, again, is the standard pattern of how at least the more massive galaxies evolve. This is not some kind of special case. Finally, the elongation of galaxies. The fact that the low-mass galaxies at redshifts below 2 and the lower-mass galaxies 10 to the 9 to 10.9, 9.5 at redshifts between 1.5 and down to 1 at least, a majority of them are elongated. If you graph the short axis over the long axis normalized to 1 versus the middle axis over the long axis normalized to 1, if they're all equal, of course it's a sphere. If you've got two short ones, then it's prolate. If you've got two long ones and one short one, then it's disky or oblate. So this is the disky fraction, the blue fraction, and at least in the low-mass galaxies, that persists down to redshift 1 at least. How do we know this? We look at the distribution of axis ratios. This shows you the distribution of axis ratios at redshifts 1.5 to 2 in this lower mass spin, 10 to the 9 to 9.5. If you've got a disk, as I'll show in a minute, it more or less evenly populates the axis ratio space down to whatever the minimum axis ratio is. But the only way you're going to get a big peak here at an axis ratio of 0.3 is to have a large number of galaxies that only have axis ratio near 1 when you look at them end on. And mostly, when you look at them edge on, they have these small axis ratios. Sandy actually showed the basic idea yesterday, but then she didn't show the data, so I'll show the data. So this is the way spiral galaxies are going to look. Of course, they'll have a range of different sizes. That's the semi-major axis. But for any size, as you look at it in different inclinations, you're going to get this range from maximally edge on to face on. Whereas if you've got a elongated galaxy, you're going to get a path that looks like this. It'll have an axis ratio near 1 when you look at it end on. When you look at it edge-wise or crosswise, it's going to be long, so long semi-major axis with low axis ratio. So do we see this? Yes. This is data from the two Candel's southern fields, Good South and Euclids. And you see this characteristic pattern, but you see that there's a lot of galaxies here following this prolate track. You also see the disks coming in, not so much here, these are the lower mass ones. You start to see the disks coming in, especially at the lower redshifts, and they're more evenly populating the axis ratio. So I think, again, this is robust. This is not some kind of weird thing. So do the simulations see this? And the answer is yes. The adaptive refinement tree hydro simulations that Daniel Severino's been running do see these phenomena. First of all, let me remind us that there's two different approaches that are popular these days. One is to run large boxes, 100 megaparsec or so boxes, with low resolution, kiloparsec, half a kiloparsec resolution, with all the internal processes tuned like in a semi-analytic model. And the Eagle and Illustra simulations have gotten a lot of publicity. And the advantage is you can simulate many galaxies and study populations and their interactions with the circumgalactic medium and the intergalactic medium. But the disadvantage is, because the feedback and winds are tuned, we learn little about how galaxies themselves evolved, and we cannot compare in detail with high-res galaxy images at high redshift. the advantage of this approach is you can make these kinds of comparisons, but the disadvantage is you can't run a statistical sample. It's too expensive to run these simulations in large numbers, although that's going to get better. So one approach, which we're trying to follow, is to put the simulation insights into semi-analytic models, which then, of course, can do 1 million galaxies in a short time. So the adaptive refinement tree simulations, especially the ones that Daniel's been running, and the FIRE simulation suite are examples. And of course, this is the approach we're trying to follow in the Algora project. So that's what we're going to talk about. Now, this is the picture of the simulations that Daniel's run, and we are dividing them into 4 generations. The first generation were these higher mass halos, 10 to the 12, about 3 times 10 to the 13 H-inverse solar masses at redshift 1. These are the Vela suite. It's the same initial conditions, 35 simulations, 10 to the 11 to 2 times 10 to the 12th H-inverse solar masses at redshift 1. And they were run 3 times, once without radiative feedback, once with UV radiative feedback, and we're finishing a run with UV plus IR radiative feedback. The first generation, you've seen some of these pictures before, so these are the gas. These are sunrise versions, so you can see what these galaxies would look like close up. This is what they'd look like. This is what this galaxy would look like, and this galaxy would look like to HST. And they do look an awful lot like HST images. We also wrote papers where we looked at the Lyman alpha and also the low ion states. In general, they didn't have enough, about half as much covering of Lyman limit systems as observed, and an order of magnitude too low in silicon 2 and similar low ion states. The radiative feedback is supposed to represent what we know really happens in nearby systems like the Rosette Nebula, where no supernovae have yet gone off, but you see these O stars are clearing out the region around them. The generation 2 simulations were somewhat higher than the Baruzzi-Webster-Conway stellar mass to halo mass, but we're doing much better now. They're still a bit too high, but certainly in the right ballpark. In fact, if you look at some of the latest data, some of the data that Reinhard Genzel showed, it looks like these are really quite a good match. The third generation, the ones with the radiative pressure feedback, preserve much more gas, especially at lower redshifts. So these are the first generation, second generation, third generation, much higher gas fractions. So they form fewer stars at high redshift, preserve more gas, they can form more stars at low redshift. That seems consistent with observations. When you have the radiation pressure, you tend to have smaller clumps. You have the same number of large clumps, but fewer small clumps. You also tend to get more elongated systems. When we sunrise these images, we take the high-resolution sunrise output, and then we candleize. In other words, we repixelize with the same pixel scale and lower resolution and add noise. And we add real noise from HST images, so they look like HST images. And then we run these things through the same analysis procedures that the actual galaxies have been run through. So this is the sort of thing that we get. And you can see that in rest frame UV, these are still pretty clumpy. These would be considered clumpy galaxies. Question was, when you turn on the radiative feedback, does that destroy the clumps? And the answer is it doesn't have much effect on the massive clumps. As Nir Brandelker explained to you yesterday, it does tend to destroy quickly the clumps less massive than about 10 to the 8 solar masses. These are very massive things, these clumps. This was the data. This was the prediction from the simulations of how the age would change, and reflected here in the color, as the clumps move in. And this is an example of how Yiqing Guo is comparing the candleized images to the simulations. And what we're seeing is that often there's not a one-to-one correspondence between clumps in the high-res simulations and in the candleized images. So I don't have time to go into the details, but basically we are picking up what seem to be the appropriate phenomena. This is the compaction story, again, the summary picture, and you see the more massive galaxies they compactify and quench and grow, compactify, quench, and grow. The low mass galaxies make efforts to compactify, they try, and then they finally end up in this diffuse quiescent zone. This is Avishai's summary of how this all works. So the gas mass grows, the stellar mass grows, they cross, you get more stars in the center. This is the inner 1 kiloparsec. You have a gas flow that's more rapid than star formation. So gas accumulates in the center. You get this burst. Here's the sort of cartoon summary at 1 kiloparsec and the eventually whole galaxy at 10 kiloparsecs. This is from a paper that I think is now on the archive. It's submitted, led by Sandro Tequila, stacking the low mass and intermediate, or the high mass and intermediate mass. And here you see this sharp decrease in radius. These galaxies have an effective radius that decreases by a factor of 2 or more. That's the compaction phenomenon. And you see that it occurs when the stellar mass reaches and exceeds about 10 to the 9.5. That's the compaction. The lower mass galaxies don't compact because they don't get up to this the first several tries. Now on to elongation. So this is the stars, this is the gas. Sorry, this is the dark matter, that's the stars, no gas. And we've been saving 1,000 or 2,000 time steps every 5 million years or so. So we can make these beautiful movies, and then every so often we can sunrise them. And so what you see is the dark matter is highly elongated, more elongated in the center, rounder on the outside, and the stars are following the dark matter. And I could let this run and run. I showed you what the redshift 1 looks like. This is face on. But actually kept it the same viewing. So, whoops. So that's what it looked like. Doesn't want to go back. Okay. So this summarizes the story. This is the stars. That's the dark matter at redshift 2. End on, edge on. And what you see here, this paper is already accepted for publication. It'll be out any day, and it's on the archive. And what you see is that this is the dividing line between being dark matter dominated and being star dominated. And this is elongated at this end and round at this end. And so the picture is that when you have the compaction process and the baryonic mass exceeds the dark matter mass in the center, then they become round. And it seems that this is the case with every single galaxy. They're virtually all elongated, except for the more massive galaxies. This is something that we would see only with JWST, because it's going to happen at redshift 4 or even higher. And this is one of the plots from the more detailed discussion of this by Matteo Tomasetti, whose talk on this was a couple days ago. We've also run these things through sunrise and candlelize them, and we're seeing this elongation pattern. So the ART hydro simulations do produce these 3 phenomena, but are the simulations reliable? Do we have the right adequate resolution? Have we done resolution tests? On the whole, the answer is no. Feedback. Is our feedback realistic? Well, pretty realistic. Is it realistic enough? I think until other simulations produce these phenomena, and we realize that it's not a simulation-dependent issue, I think that we and other groups are right to question these things. And then finally, of course, the reason that we do these simulations is ultimately to understand what's happening. Do we understand where the clumps come from? I don't think we fully do. As Nir Mandelker explained at the end of his talk yesterday, and as Avishai mentioned, the region that's going to turn into a clump has Q greater than 1. In other words, it's stable. What causes compaction? There are a number of different processes. How could we tell which are acting in individual galaxies or even groups of galaxies? Elongation does appear to reflect the filamentary nature of the cosmic web. So finally, what we want to do is have groups that are running high-resolution simulations compare their techniques by running them on the same initial conditions. And so we started several years ago this Assembling Galaxies of Resolved Anatomy program, co-led by Piero, who's standing in the back, and me, and with a number of leading figures in the field as the coordinating committee, initial conditions for all the simulations, and an isolated spiral galaxy at redshift 1, a Milky Way roughly. We're about to submit this paper. It's going to be finished, we hope, or largely finished this weekend at the Agora meeting. UV background, the Grackle cooling code are now adopted by everybody. Tools to compare simulation based on YT for all the codes. And of course, this is useful for everybody, not just, of course, for the Agora 8 initial conditions, but for everybody's use. And we hope to very soon have the YT to Sunrise pipeline working so that anything that can be analyzed by YT can be automatically run through Sunrise with all the bells and whistles. The paper describing the project and giving some of the first tests was published already in 2014, led by Ji-Hoon Kim, who's in the back of the room, and who's going to be the coordinator for this weekend's meeting. And we have many different working groups. These groups are largely finished setting things up, and these groups are just beginning to act. So that's what I wanted to say. I hope there's time for some questions.
Sandy? I wonder if you can go back to the slide that you showed, which showed our axis ratios, and you drew this prolate curve in all of the diagrams. Because I'd like to clarify something that I think I probably didn't say very effectively yesterday.
There we are.
Okay, so
Let's look. Shall I put in this one with the disks part highlighted too?
well, I think as I heard your words this morning, I think you were implying that the prolate track is actually physically present in every one of those panels. And that's not my interpretation. My interpretation is that that is a strong role when there's no strong disks. But in the upper row, for example, when we have disks, and we populated the disk corner, I think a better model is that we have a whole bunch of disks, but when we find small disks, they're rounder intrinsically than larger disks.
Okay.
Obviously, looking at a distribution like this and trying to tell the difference is going to be extremely difficult and require lots of galaxies.
What I wanted to emphasize, I didn't want to really talk much about the disks. What I wanted to emphasize was that you see a heavier weighting of points on the prolate track.
That's exactly what you expect.
If you have disks becoming significantly smaller, but then wouldn't you?
You generally expect more objects. Those are the objects that were not at zero. Those are the disks with finite flattening, and they got moved up and they make a ridgeline. And that ridgeline is very hard to tell in the prolate ridgeline.
So the two comments. One, this is data from only the two southern Candles fields. We have now in hand data from, I think, all five fields. So the statistics will get better. And as Sandy's saying, you can't do this by eye. You actually have to do a detailed analysis, and that's underway.
So along this line, I'm trying to understand why you guys keep hammering on the prolate track thing. Isn't this sort of also consistent with just having disks with bulges, and bulges are more prominent in the smaller disks?
Absolutely.
Right. That's why you have to be more careful to try to see what's really going on.
What's interesting is that the high redshift distributions really don't look as though they're disk populated.
So that's the second point that Sandy wanted to make.
That's what I'm trying to say.
Right. That's not what I was trying to emphasize. But it's another key point, which is that there's a lot of structural evidence, but also kinematic evidence that disks really only come into their own. First of all, first at high masses, but even at high masses between redshift 1 and 2, not really above redshift 2. And then there's this disk settling phenomenon that occurs first at high masses and then at lower and lower masses, where the ratio of rotation to dispersion grows. And that's That's the kinematic aspect.
I have a comment on simulations. So if you or anybody have simulations throwing a lot of parameters, many of which are very uncertain, then you get simulation that fits everything. What do we learn from that?
Okay, I think that's an important thing to appreciate. Thanks for the question, Renyu, is that that's not at all what we did with these simulations. In no sense were these simulations run in order to produce these phenomena. In no sense was that the case. What happened was the simulations were run to try to do the best job we could with the available resources, including computer time. We looked at the simulations, and we found, lo and behold, they had these phenomena. All of the simulations I described, all three phenomena, the clumps, the compaction, and the elongation, were seen first by the observers, and then when we looked at the simulations, they were there. We didn't fiddle with the simulations. We didn't try. As we turned up the feedback to make them more realistic and give us a stellar to halo mass ratio more in line with the abundance matching, we were worried that that was going to destroy the clumps, for example, but it didn't, not the ones that we see.
I have a question regarding the selection strategy of your halos. So since you're performing a zoom and you have a limited number of zoom-in simulations, in order to recompare with the Campbell's sample, how do you make sure that you're comparing apple with apples in terms of halos, of accretion histories, or
Great question. So the answer is it's not a statistical comparison. The halos were simply chosen at random to represent a uniform distribution in log mass. Daniel's going to explain in more detail.
Yes, I was going to say the same, that it's a random selection. We only avoid things like a major merge at some point at the latest redshift.
So there's an isolation criterion at redshift.
So it's a very mild isolation criterion.
Let me explain that we're now, first of all, the code's been tremendously sped up by more than a factor of 10. And so we now can run to redshift 0 quite rapidly. And our new strategy is that we're going to select halos, again, in mass bins, but at each mass, we're going to select across two different key parameters. One is concentration, and the other is lambda. So that we're going to do a better job of sampling. Looks like my time is up.
No, I have a question. Hello. Very quickly. I like very much these prolate structures, of course. And I was wondering, I always thought it's kind of natural that you get a prolate structure. The reason is if you have a strongly self-gravitating disk and no bulge yet, then naturally the disk becomes unstable to bar formation.
This is completely different from the bar. So the referee asked the same question, and we explained to the referee in great detail. And also, the same question was asked yesterday, and the answer was also explained in great detail.
Sure.
These are not bars. Bars occur, just as you say, in strongly self-gravitating disks. These do not have any disks. They have low-mass gaseous disks. The centers are totally dark matter dominated. As soon as the centers cease to be dark matter dominated, they become round.
Good.
So it's a completely different phenomenon. This is not the bar phenomenon. Okay, time to move on. Whoops.
Your microphone.
Yes.
So I let that go kind of long because
the higher mass galaxies, and there's a sort of a downsizing phenomenon. The higher mass galaxies start to quench and become less star forming and less clumpy as you go down to lower redshift. But the key thing to appreciate is this is not some kind of weird special case. This is the majority of all star forming galaxies. Also, this is data from the paper Yiching led in 2012. There's a lot better data that continues to support this. And that is that the colors become progressively redder as the clumps are seen closer to the center of the galaxy. So there's at least presumptive evidence that there's an effect where the clumps are moving in. That's what the simulations show. And as they form, they're young and not very metal rich. And as they move in, they become older and more dusty and higher metallicity, etc. The key thing was the ability to use the wide field camera 3, and in particular its infrared capabilities, which go to 1600 nanometers. So, in other words, H-band. This means that we can see blue light all the way to redshift 3 and pretty much the whole visible spectrum to redshift 2. So we can see old stars, not just the UV light in rest frame, from young stars. That's been the key. This is the high noon period, as we called it in our popular article, and cosmic dawn, which is accessible, of course, from the UV. This is an image from the McDowell and Dickinson Review in annual reviews, and the little yellow boxes are the region that HST has basically touched. Second point is compaction. So by studying basically the same cosmic volume at 6 different redshift intervals, the Barrow et al. 2013 paper showed that there's a motion. Of course, you never see an individual galaxy doing this, but you see the population move from diffuse star forming to compact star forming, blue nuggets, to quenched star forming, red nuggets, and then those tend to get bigger. And then there's the slow track where galaxies never get into this corner and just slowly fade and grow. This tends to be more of the spiral galaxies. This tends to be the galaxies that have bright, bulgy centers. This was the key figure from the paper led by Guillermo, starting down here, redshift 2.6 to 3. Very few in the quenched region, with both advanced camera for surveys and then also wide field camera 3 as part of these larger survey regions that many other instruments have also taken data from. So first, clumps. The clump phenomenon has been seen for decades. It was especially emphasized by the Ellen-Greens. But now, with candles, we can really get a sense of how common it is. This is a slide from Yiqing Guo's talk yesterday. And let me just highlight the 2 key things that Yiqing told you. The first is that about 60% of star-forming galaxies are clumpy at redshifts of 2 to 3. So these are the more low-mass galaxies, 10 to the 9 to 10 to 9.8 solar masses, the intermediate mass up to 10 to the 10.6, and
Joel Primacks, who's going to talk about comparing observed galaxy evolution with simulations.
so what I want to do in this talk is summarize a number of the things that have already been mentioned at the workshop regarding key processes that we now know occur in most galaxies as they evolve across the cosmic high noon period. The 3 key aspects that seem to be a ubiquitous, robust phenomena are clumps, compaction, and elongation. I'm going to emphasize the discoveries made as part of the Candels program, but of course these things have been seen by essentially every program that's looked at galaxies at this epoch. So Candels is the biggest project in the history of Hubble Space Telescope, and it's also, I think, by far the most influential in terms of number of papers, number of citations.